Hello everyone, welcome to another section. Today we shall be looking at Physics Paper 2, Variance 2, May, June 2023. So let's look at it. The first question, we have to define pressure. That's the first question. We have to define pressure. How do you define pressure? Okay, so let's write it down. So pressure is the force. Pressure is the force. Pressure is the force applied perpendicular. Pressure is the force applied perpendicular to the surface of an object per unit area. It's important to reflect the word perpendicular. We are just fortunate that it's a 1-mark question. Assuming it's a 2-mark question, these are things they are looking for. Perpendicular. The force applied perpendicular to the surface of an object per unit area over the force is distributed. This is quite simple. It's acceptable. The next question, we have to use the answer, that's definition of pressure, to find the SI base unit of pressure. What's the mathematical formula for pressure? It's force over area. So base unit of force, force can be mass times acceleration. It can be anything, but this is a general one. Over area. Mass is kilogram. Acceleration is meter per second square. Area is meter square, which is meter times meter. Meter cancel meter. So we have kilogram multiplied by s minus 2 multiplied by 1 over m, which is the same thing as kilogram s minus 2 per meter. This is what they asked us to prove. SI base unit of pressure. Now the next question, B. A horizontal pipe has a length L. A horizontal pipe has a length L and a circular cross section of radius R. A liquid of density P flow through the pipe. The mass of the liquid flowing through the pipe is in time T, is given us this, where P1 and P2 are the pressure at the end of the pipe and K is constant. You have to find the SI base unit of K. Now to find the SI base unit of K, let's make K the subject of formula. When you make K the subject of formula, first by cross multiply. When you cross multiply, you end up having 8mKL equal to pi P2 minus P1 R raised to the power 4 density multiplied by time. So make K the subject of formula. That will be pi P2 minus P1 can be written as change in P, R raised to the power 4 density multiplied by time over 8 ml. Pi is a number, it has no unit. 8 is a number, it has no unit. So we don't have any business with such. So K will be, now change in P is pressure. And what is the SI unit of pressure? As you can see earlier, is kilogram, S minus 2, M raised to the power minus 1. Radius, R is radius. Radius is meter, meter raised to the power 4. Density, now density is mass over volume, right? Density is mass over volume. That will be kilogram per meter cube. So density is kilogram per meter cube. That's density. Time is seconds. All over M should be mass according to the question. So M is kg. L is length, that's meter. So from here, K will be, let's do some cancellation. Kilogram, cancel kilogram. And so this is S minus 2, S minus 2, and S. So S minus 2 and S, that will give us minus 2 plus 1. That will give us S minus 1. This is M minus 1 and M minus 3. That will give us M minus 4. We still have another M raised to the power 4 there. And we have kilogram up all over meter. This M minus 4 and M plus 4, they are out. So what is left for K? We have kilogram, we have S minus 1, we have kilogram, we have S minus 1, and we have 1 over M. So which is, so the answer will take kilogram, S minus 1, M raised to the power minus 1. That's the SI base unit of K from the model expression. The next question, an experiment is formed to determine the value of K by measuring the values of the other quantity in equation B. The values of L and R as percentage uncertainty. So percentage uncertainty of L is the same thing as percentage uncertainty of R, and the value is 2%. State and explain quantitatively which of the two quantities contribute more to percentage uncertainty in K. So don't forget our K is modeled as I think we have change, let's see it. K is change in pressure, radius raised to the power 4, time, and density all over ml. None of them, when you compare, is about L and K. So it's about L and R. Let's ignore everything and bring L and R out first. R is on top, L is down. If I'm to find change percentage uncertainty in K using R and L alone, I will have something like this. 4 change in R over R plus change in L over L. And remember that Percentage uncertainty in R is 2%. L is 2% too. So for R is 8%. So which means R contribute more. R contribute more because, okay, let's write it down. So the conclusion is R contributes more because R at the end of the day R is 8% after calculating, while L contributes 2%. That is what I can deduce there. That's the answer. Number 2, state what is meant by center of gravity. Okay, that's the general. What's the general definition of center of gravity? The point. Okay, the point where all the weight, the point where all the weight, the point where all the weight of an object is taken to act, is called center of gravity, or the point where the weight of an object lies on, where all the weight of an object lies on. For example, now a meter rule mostly balance at 50 centimeter mark of the meter, or 49.5. It balance, which means all the weight of the meter rule lies at 50 centimeter. That's the meaning of center of gravity. So the point where the weight of the object can balance, that point is called center of gravity. Question B, 2 blocks are on a horizontal beam that is pivoted at the center of gravity as. So look at the diagram now. We have a block of weight 54 Newton is acting down at a distance 0.45 meter from the pivot. We have another weight 2.4 Newton is also acting down at a distance 0.95 meter from the pivot. And we have a distance 0.35 meter where a string is used to tie the beam to the ground at an angle of 30 degrees, as you can see. So the question said that the beam is in equilibrium. Yes, it must be in equilibrium because there's a string tying it down to the ground, and mathematically the weight has been placed in such a way that they are balanced. By taking the moment about the pivot, this is the pivot, as you can see. Calculate the tension in the string. Okay, now how many forces do we have there? This is one force, 54 Newton is the force acting down, 2.4 Newton is the force acting down. But we have tension force too. It's acting at a particular angle. You must resolve it. So let's resolve that force. You must resolve it. Let's resolve it vertically. This is it. This is the vertical part of it. I don't know this point AB. I don't know it, and that's what we're looking for. The vertical force. So let's use SOHCAHTOA. Sine 30. The opposite is AB. The hypotenuse is T. So AB is T sine 30. So this force acting down to is T sine 30. Now it's been resolved, so we can now calculate the value of T by taking the moment at the pivot. What is the meaning of taking the moment at the pivot? which means the direction of all the forces will go toward the pivot using the principle of summation of anti-clockwise moment must equal to summation of clockwise moment. This is the principle of equilibrium. At equilibrium, clockwise moment must be equal to anti-clockwise moment, or vice versa. Now, which one are clockwise? Clockwise, anti-clockwise. Okay, clockwise is direction of clock. Okay, anti-clockwise is anti-direction of clock. So the clockwise. Okay, let's see like this. From the diagram. So the clockwise, this force T sine theta toward the pivot is clockwise. 2.4 Newton toward the pivot is also clockwise. 54 Newton toward the pivot is anti-clockwise. Remember the question said you should take the moment at the pivot. So that's what I'm saying, toward the pivot. So distance between 54, moment is force times perpendicular distance. Don't forget. So 54 Newton toward the pivot, that's 54 multiplied by the distance between 54 and pivot is 0.45, equal the distance between T sine 30 and pivot is 0.35 plus 0.95. It covers both of them. Plus the distance between 2.4 Newton and the pivot is just 0.95. Okay, so let's do our mathematics. So 54 times 0.45 will give us 24.3. So T sine 30 times that. Okay, that's what you're going to give us. 0.5. So that one will give us T sine 30 times what is in the bracket. Give us 0.65 T plus 2.4 times 0.95 will give us 2.28. Do your maths. So our T will be 24.3 minus 2.28 divided by 0.65. So we have our T to be 34 Newton. That will be value of T. Now let's move to the next question. The string is now cut so that the beam is no longer in equilibrium. Look at it. They cut the string. So obviously when they cut this string, and they cut it, the beam will fly off, right? When they cut it, it will fly off and move towards the heavier beam or the heavier weight. It will fly off and move toward the heavier direction. So the question now asks us, calculate the magnitude of resultant moment. So in this case, we have the forces on the beam now. Most likely will be the anti-clockwise moment on the left, which is 54 times 0. Let me see it. 54 times 0.45. So that gives 24.3. And the other one will be the clockwise moment on the right, which is 2.4 multiplied by 0.95. That one will give us 2.28. T is no longer there. It's no longer in the picture because it's been cut off. So the question asks us to find the question. So the resultant moment in this case will be 24.3 minus 2.28. So the resultant moment, so 22.02, that's 22 Newton meter. That's it. Next question. The beam in B rotates when the string is cut. Yeah, it will rotate anti-clockwise. Okay, let me show you. It's going to rotate like this because it will move when the string is cut. The beam will move like this, anti-clockwise, because the heavier weight is in that direction. So the small block of weight 2.4 Newton is projected through the air. When the string is cut, this 2.4 Newton weight will fly off. This 2.4 Newton weight will fly off because this string has been cut. It's expected to fly off. According to the question, they said it fly off through the air. Now, the diagram below shows the parts of the parts, the last part of the block before it hits the ground. You know, the block will fly off, as in they use the word "is projected," which means that it moves up like this before coming down when it reaches maximum height. So this is the part the question shows, MN. This is the part they show us. This part is the part when the 2.4 Newton is coming back. That's the one they show us. The point X on the part at X, when it's coming down, at this point the block has a velocity of 3.4 meter per second, and at that point the height is 1.8, as you can see above the ground. Air resistance is negligible. Calculate decrease in potential energy of the block as it moves from X to Y. At Y, there is no height. At X, there is height. So, potential energy at X, you have to look for it. Potential energy at X, which is mgh at X. So, potential energy at X, mg is mass times, that's the weight. The weight is 2.4. The height is 1.8. So potential energy at X will give us 4.32. That's potential energy at X. 4.32. Potential energy at Y, the same mg hy, 2.4, but at Y there's no height, it's 0. So you can see that's why they said decrease. So change in potential energy from X to Y. From X to Y will be 4.32 minus 0, which will give us 4.32 joule. That's decrease in potential energy, 4.32 joule. The next one, use the answer and conservation of energy to determine the kinetic energy of the block at Y. Now, according to the principle of conservation of energy, total energy at X, if there is no resistive forces, must be equal to total energy at Y. What is total energy at X? Kinetic energy at X plus potential energy at X. What's total energy at Y? Kinetic energy at Y plus potential energy at Y. Now, what's the kinetic energy at X? That's half m mvx squared. Potential energy at x, mghx. What's kinetic energy at y? That's what we're looking for. Potential energy at y is 0 from the previous analysis. So from here, so we have half. What's mass? Remember that weight is mg. Mass is weight over g. And the weight we are talking about is 2.4 over g, 9.81. Multiplied by speed at x, I think it's 3.4 squared, plus mgh at x is 4.32, equal to kinetic energy at 1. So from here we have 2.4 divided by 9.81 multiplied by 3.4 times 3.4 at the square multiplied by 0.5. We have 1.41. Let me do it again. 2.4 divided by 9.81. So this gives us 1.4141 plus 4.32. That will be kinetic energy at y. When you add them together, you're going to give us 5.7. That's the kinetic energy at y. Question 3. State the variation, if any, in the direction of acceleration of the block. Acceleration when it's coming back as it moves from x to y. Acceleration is always vertically downward now. So let's put it vertically downward when it's coming down. Next question. The block passes point x at time tx and arrives point y at time ty. Sketch the graph to show the variation of the magnitude of horizontal component of velocity. Horizontal component of velocity from tx to ty. When the body is projected upward or projected, anyway, gravity has no effect on horizontal component. It's constant from the beginning to the end. If it's vertically, it's only vertical direction that has effects, that gravity has effect on. But horizontal component from the beginning to the end is constant all through. So the graph is expected to be a non-zero value that is constant from tx to ty. This is the graph. Next question, number 3. A block is pulled by force x in a straight line along a rough horizontal surface as shown in figure 3.1. Assume that total resistive force opposing the motion of the block is 0.8 Newton at all speed. So total resistive force is 0.8 Newton at all speed. So let's take note of that. Resistive force is 0.8 Newton, which means that the resultant force on this block in question is x minus 0.8. Take note of this. This is the resultant force on this block, x minus 0.8. So look at the variation of force with time. The first question asks us to define force. Okay, the best way to define force in this case is to relate it to change in momentum. So Newton's second law of motion. Force is the rate of change in momentum. Force is the rate of change in momentum. That's the best way to define force. Rate of change in momentum. What I mean is this: force is rate of change in momentum. That is mv minus nv over time. Rate of change. Next question. Determine the change in momentum of the block from 0 to 3. Okay, what's the formula for change in momentum? Change in momentum can be mv minus mu. Change in momentum can also be impulse of a force times time. When you check this question, the question did not mention anything related to mass. I think we can still play around force times time. So let's use that. Between 0 and 3. Let's go back to the graph. Between 0 and 3, the time is 3, right? Between 0 and 3, what is the change in force? At 3, the force is 0.8. At 0, the force is 1.4. So we have a change in force at 1.4 minus 0.8. So change in momentum in this case. So force is 1.4 minus 0.8. Why the time is 3 seconds between 0 and 3. 3 minus 0 is 3. So at the end of the day, what do we have as our change in momentum? So 1.4 minus 0.8 multiplied by 3. So change in momentum will give us 1.8 kilogram meter per second. That's change in momentum. Describe the motion between t equal to 0 and t equal to 6. Now let's go back 2 marks, 2 points. If more than that, if you have more than that, put it. You can't tell. Between t equal to 3 and t equal to 6, check it. This point, the force is constant. Force is constant at 0.8, does not change. Remember that once force is constant, then what causes force? What brings about force? Acceleration. So since force is constant, okay, let's talk about that. Since force is constant, remember that our resultant force is x minus 0.8 from the beginning on the object. So resultant force, in this case, our force here is 0.8 minus 0.8. So since force is constant, resultant force will be equal to 0. So once resultant force is 0, which means that there is no resultant force, velocity is constant. Velocity is constant. Since there is no resultant force, velocity is constant. So let's put it down there. Describe and explain between, let me put it like this, between 3 seconds and t equal to 6 seconds, comma, the force x equal to 0.8 is constant all through. I'm writing what I saw all through. It's constant all through. Hence, resultant force will be 0. Why? Because from initial model, resultant force is x minus 0.8. So x will now resultant force will now be 0.8 minus 0.8. So which make it constant. Hence, resultant force is 0. Since resultant force is 0, velocity is constant. That's it. There's no change in velocity. So velocity is constant. And also acceleration will be 0. Velocity is constant. I think this will be enough. Figure 2. Force X produces a power of 2 watts. Calculate the distance. Okay. Remember that power can be FB, force times velocity. Since in this case velocity is constant, so the formula for velocity will be distance over time. We are looking for the distance, so power is Fs over t. Calculate the distance. So when equals multiply, Fs equal to Pt. Make S the subject formula, Pt over F. So let's get our distance. Distance, power is 2 watts. The time between 3 and 6 seconds. Between 3 and 6 seconds. So our time will be 3 seconds. 6 minus 3 divided by force. The force between 3 and 6 seconds we've seen down for is 0.8. So let's get our distance. 6 divided by 0.8, 7.5 meter. So our distance is 7.5 meter. So we write 7.5 here. There is meter there. That's it. Next question. The block is now at rest at time t equals to 0. On figure 3.3, sketch a graph to show variation of momentum of the block with time t from t equals to 0 to t equals to 6 seconds. The numerical value of momentum are not required. Oh, okay. Remember that. Let's work like this. Don't forget our resultant force. Let's work like that. What we did earlier. Remember the resultant force on the model is x minus 0.8. This will help. Now, the graph of momentum against time is describing force, because force is rate of change of momentum. So when you plot a graph of momentum against time, it's describing force. So between 0 and 3, what do you notice between 0 and 3? Between 0 and 3, what's our force? Force is 1.4. And after 3, it decreases 0.8. See it? Between 0 and 3, our force is 1.4. So between 0 and 3, force is 1.4. That's x, the value of x, which is force 1.4. So resultant force is 1.4 minus 0.8, which will give us resultant force at that point between 0 and 3, 1.4 minus 0.8. So resultant force between 0 and 3 is 0.6 Newton. So momentum is Ft. So at 0, momentum will be 0. At 1, when t is equal to 1, momentum is force 0.6 times 1. At 2, momentum is 0.6 times 1.2. That's 1.2. At 3, 0.6 times 3. Remember, no numerical value is needed. At 3, momentum is 1.8. Where you check it, from 0 to 0.6 to 1.2 to 1.8. Look at the increase. The change is constant. 0.6, 0.6. The change, they are increasing anyway. The value of momentum between 0 and 3 is increasing, and the change is constant, which means the gradient is constant. So it's going to be a straight line with a constant gradient. That's why I worked that one out. From 0 to 3, the straight line with a constant gradient. That means all the values required. This is it. It's a straight line from 0 to 3 with a constant gradient. Now from 3 to 6, remember that the force decreases. X now turns to 0.8. So from 3 to 6, resultant force is x minus 0.8. So 3 to 6, x is 0.8. So resultant force from 3 to 6 is 0 all through. So momentum, remember that momentum is Ft. Since resultant force is 0, all through momentum at that point through is 0. But so which means if momentum is 0, it means that it's constant all through. Because if change in momentum is 0, yeah, change in momentum not 0, which means that on this place it will be something like this. Because the resultant force is 0. Since the momentum is constant, change will be 0. So this is how the graph will look like. I believe it's clear. If you have any question, let me see it in the comment section. Number 4. A spring is suspended from a fixed point at one end. The spring is extended by a vertical force applied to the other end. The variation of force against the L is this. Okay, look at this graph. The graph starts from 8. Do you know the meaning of this? It means that when L is 0, that's x-axis, the force is 8. Which means when x is 0, the force is 8. When L is 0, yeah, L is 0, no length. So original length is the force 8 Newton at 0. So they asked us to state the name of the law that give relationship. State the name of the law that give relationship. Hold on, no. Let me rephrase this. Sorry. This point means this point, as in this point, this place is 8 and 0, yes. You know, this is L on the x-axis, F on the y-axis. So which means when the force is 0, L is 8. So this 8 is the original length then. The original length is measuring centimeter from the graph. Okay, let's move on. State the name of the laws that give relationship between force and extension. Hooke's law. Mr. Hooks or Mr. Robert Hooks. Determine the spring constant. Okay. The graph of F is plotted against L. Yeah, so from here, the gradient should be the spring constant when the graph of F is plotted against L. So the gradient is the spring constant. Okay, let's find the gradient. The gradient will be change in F over change in F over change in E, or over extension. Anyway, the gradient of this graph is K, that's change in F over extension. Hooke's law is F equal to KE. So K is F over E. That's it. So from the graph, let's go back to the graph. The force is 12 and 0. So from here to here is 12 minus 0. Right from here to here is 24 minus 8. So the gradient. So therefore, E will be 12 minus 0 over, what's 24 minus 8? 24 minus 8 should give us 16. Remember, it's in 24 minus 8 is 16. Remember, it's in centimeter. Convert it to meter. 16 divided by 100, 0.16. So K is 12 over 0.16. So 12 divided 0.16, we have 75 Newton meter per meter. That's it. Let me make it here. 12 minus 0 over 24 minus 8. The next question. Determine the elastic potential energy. The formula for elastic potential energy is R kx squared. So elastic potential energy is R. Our K is 75. What's the extension? X the extension. Extension is new length minus original length. So elastic potential energy when the force is 6 Newton. Let's go back to the graph. When the force is 6 Newton, what's the length? When the force is 6 Newton, the length is 16. So F 75. When the force is 6 Newton, the length is 16. So the new length is 16. The original length is 8, like I said earlier. So elastic potential will now be half times 75. 16 minus 8, that's 8. It's in centimeter. Take it to meter. That's 0.08. 0.08 squared. So multiply by 75 times 0.5. So our elastic potential energy is 0.24 joule. That's it. The next question, number 5. A progressive wave travels through a medium. The wave causes the particle of the medium, okay, the particle of the medium to vibrate along line. The particle vibrate along line P, while energy vibrate or propagate along Q. Compare the direction of lines of P and Q for transverse. For P and Q for transverse, which means they are perpendicular. If you remember transverse wave, the direction transverse wave can be defined as a wave in which the direction at which the particle travels is perpendicular to the direction at which the energy propagates. The particle and the way energy moves, they are always perpendicular to each other. The key word. So compare P and Q if the wave is transverse. It means they are perpendicular. For transverse, P and Q, they are perpendicular. For longitudinal, then the direction of particle and the way energy propagates must be parallel. For longitudinal, it means P and Q, they are parallel. The question represented P and Q as direction of travel of particle and direction of propagation of energy. So just figure out the terms there. That's all. Question B. A tube is closed at one end. A loudspeaker is placed near the other end, as shown. The loudspeaker emits a frequency of 1.7 kHz. The speed of sound in air in the tube is 340 meters per second. Stationary wave is formed with antinode A at the open end of the tube. There is only one or other antinode A inside the tube. It makes the work easier. Which means there are two antinodes all together. If I'm going to sketch this stuff, it's going to be like this. If there are only two antinodes, it's going to be like this. I'll do it in such a way that I only have just two antinodes. This is the possibility. So determine the wavelength of the sound. Since V equal to F lambda, wavelength is V over frequency. V is 340. Frequency is 1.7 kilohertz. 1.7 times 10 to the power 3. That's the frequency. So if you use your calculator, so wavelength will give us 0.2 meter. And you put this in your calculator, it gives us, it gives us 0.2 meter. The second question, we have to determine the length of the tube. Okay, the length of the tube, look at it here, is equivalent to this. This antinode, this is node, antinode, this is node. How many? This antinode to node 1, node to antinode, the same thing 2, antinode to node 3. So we have 3 nodes to antinode that make up the length. So our node to antinode is lambda over 4, so equal to L. So L is 3/4 of lambda, and lambda is 0.2. So that gives us 0.15. That's the length. The next one. Next one is this. The maximum wavelength of the sound from the loudspeaker that can produce stationary wave in the tube. Maximum wavelength. Maximum wavelength. Maximum wavelength. It's not fundamental frequency. The loudest. Okay. For this tube, open tube. For open tube, what's the fundamental frequency? Let's see. For open tube, the fundamental frequency is just this antinode to node. So lambda over 4 equal to L. Lambda is 4L. Fundamental frequency is V over lambda. In this case, fundamental frequency is V over 4L. Yeah. So fundamental frequency is V over 4L. So the maximum wavelength will be 4L. That's the fundamental. The maximum wavelength is 4L in this case for open tube such that one end is closed, the other end is open, and L is 0.15. 4 times 0.15. What do you have? You have 0.6. That's the maximum wavelength. 0.6 meter. Question C. 2 polarizing filters are arranged so that the planes are vertical and parallel. Okay. The first filter has a transformation at an angle of 35 to the vertical. This. The second filter has a transformation alpha to the vertical as shown. Okay. This one is this 8.5, the incident intensity, to produce after passing through the filter to produce a transmitted intensity I1. So this I1 will enter the second filter. We enter the second filter as I0, as another I0, and produce another transmitted intensity of I2. So let me stick to that step. I'm coming. I'll come back to this. So the question says alpha is greater than 35. This angle alpha is greater than 35 and less than 90. We don't know it then. It's greater than, all I know is that the alpha is greater than 35 and less than 90. Okay. Less than 90. Alpha is greater than 35 by what? I don't know. It's greater than 35 by what? By which angle? It's greater than 35 by what? I don't know. Greater than 35 by what? I don't know that theta 1. So which means to get alpha, I must get theta 1 first. Alpha is greater than 35 by what? Theta 1. I don't know it. I'm coming. A beam of vertical polarized light of intensity. A beam of vertical is normally incident on the first filter. Like I said, this is I0. Show that the intensity of transmitted, the transmitted is I1 by the first filter. Show that is this. So using Malus theorem, using Malus law, in this case to be I1 equal to I0 cos square theta. So I'm looking for I1 anyway. So I1 is I0, that's intensity, the incident one, 8.5 cos theta. Theta is 35 in this case. All squared, that's the meaning. So at the end of the day, 8.5 cos 35 all squared. So I1 will give us 5.7 Weber per meter squared. So that's it. Now the second one, the intensity of the light transmitted by the second filter is this. Now the intensity of the light transmitted by the second filter, this is what comes out of the second filter. Remember that I1 for the second filter will be the I0. So which means that this Malus theorem, which is I equal to I0 cos square theta, for this one, what is transmitted here is I2. The incident for the second filter will be I1 cos square theta. I remember the condition for this filter, that angle alpha is greater than 35 by the value, I don't know, that's the value I want to look for before I can get alpha. So I2 is 5.2, I1 is 5.7 cos square theta 1. So cos square theta 1 is 5.2 over 5.7. So cos theta 1 squared, that means of cos square theta 1 is 5.2 over 5.7. 5.2 divided by 5.7. I have 0.9123. So cos theta 1 is square root of 0.9123. The square root of 0.9123 give me 0.9551. Theta 1 will be arc cos of 0.9551. Second function cos 0.9551. I have 17.2. So since alpha is 35 plus theta 1, so alpha in this case, theta 1 is 17.2. Alpha in this case is 35 plus 17, which gives 52 degrees. That's it. Let's move to the next one. Number 6, electricity. The current in the filament decreases. Oh, this is about filament lamp. Now let me quickly shed some light about filament lamp. Now, so these are non-ohmic conductor. Anyway, filament lamp, non-ohmic conductor. The graph of a filament lamp usually look like this. The IB characteristics, current against voltage, for a filament lamp is always like this. I can also extend it to the other side. Now, how does a filament work? Increase in temperature. Increase in a filament lamp consists of it has a small semiconductor. They get material in it. So increase in temperature of a filament lamp. Increase in temperature of filament lamp increases the energy. It increases the energy. So once the temperature increases, energy increases. So the key to this stuff is that it also increases vibration of the lattice. It increases the vibration of the lattice. So the lattice vibrates vigorously. Because the lattice vibrates vigorously, it makes it harder. Because of this, it makes it harder. It makes it harder. It makes it harder for electron to go through the metal. Makes it harder for electron to go through. So since electron is not going through, since the electron is not going through, so there will be increase in resistance. Electron is not flowing through it's not flowing regularly. It makes it harder for electron to go through. Hence, there will be increase in resistance. Electron is not flowing through. It's not going through properly because there's vibration in the lattice. Electron is also vibrating, but they are not passing through. They are not passing through the hole properly through the filament lamp. So the electrons are not going through properly, so resistance increases. Now, the question asks us that we should find the current in filament lamp decreases. For current in filament lamp increases, he said you should state and explain how the resistance of the lamp changes. So it will be opposite of this. In this case, if current decreases, which means temperature also decreases. If current decreases, temperature also decreases. And when temperature decreases, there is little vibration of the lattice. Vibration of the lattice. Once there is little vibration of the lattice, what does it mean? It means that electron will flow through properly. Electron will flow through properly. Hence, resistance will now decrease because the electron is flowing through properly. Resistance decreases in the filament. This is a key point of how filament works. It should help. I think this small point should help you figure out what's going on. B. A cylindrical wire has a length L and resistance R. The total number of free electron charge carriers contained in volume of the wire N. Each free electron has charge E. The potential difference between the end of the wire is B. Determine expression in terms of all the symbols L, N, R, and B for current in the wire. Okay, expression for current in the wire. Okay, let's work it like this. Expression for current in the wire. So in this case, okay, remember that charge is equal to IT. So current is charge over time. Charge can also be number of electrons all over time. Remember that velocity is distance over time. So time is distance over velocity. So in this case, distance in this case is L, length of wire, over velocity. So current will be number of electron charge over time. And in this case, time is distance over velocity. So it will be number of electron divided by length over velocity, which is number of electron times velocity over L. So therefore, the expression for current in this case is NEV over length, or NVE. That's the expression for current in terms of all the symbols they've said or the access to the drift velocity. We also find the expression for drift velocity. Remember that we have equation for this. I equal to ANQV. Let me call this V naught as velocity. So this is what they want us to look for. The velocity is I over ANQ. They must be in terms of what they've said earlier. Now let's start. Since the velocity is this, then we should have this. Let me look at it. So, okay, brief velocity. Let me look at this. Current is what? Voltage over resistance. That's for current on top. Over area. This area. Let me leave it as area. N. N is number of charge carrier over volume. Yeah, N is number of charge carrier over volume. It's always like that. So multiply by charge. Okay, multiply by charge. Q is IT. Q is IT. Coming to this, Q is IT. So drift velocity will be V over R over area times N over volume is area times length. Okay, it's making sense. So multiply by IT. That's charge. Let me leave like this. I'm coming. Area cancel area. So then I have this. Okay, let's look at it from this angle. This is, we can get it also from this point, but I think I just thought of a straightforward approach without going through the drift velocity equation we know already. Okay, since he said the average drift velocity of the electron in terms of this. Okay, now let's look at it like this. Velocity is distance over time. Velocity is distance over time. The distance in this case is L all over time. That's velocity. Remember that Q equal to IT. So time is Q over I. So our velocity in this case will be L over T. T is what? Q over I, which can be written as Li over Q. And don't forget that Q is number of electrons. So, and also since velocity, and call velocity as V naught. So do not confuse velocity with voltage. Velocity is L times current. Current is voltage over resistance all over NE. So therefore NE small e, sorry. Therefore the drift velocity would be LV over RNE. Oh sorry, small e. So this is what they're asking. This makes sense. So RNE. So this is it. So in terms of what? In terms of L, V, R, resistance, N, which is contain the volume of the wire is N, which is volume N, and also E. So this is what they're asking us. The next question. So let me write it here. LV over RNE. The next one is average time taken. Average time taken to move along the full length of the wire. Now, average time taken. What's the formula for time? Time is distance. Time is distance over velocity, or can also be charge over current. Anyone? It's correct. So from here, time, the distance here is L. Velocity is what we obtained before. LV over RNE. So in this case, the time will be RNE L over LV. L cancel L. So the time is RNE over voltage. That's the time. The next question, number 7. I think that's the last question. Oh, we have 2 more questions after this. A battery of EMF 9 volts and negligible internal resistance is connected to LDR. Okay, LDR is connected to LDR. So the question asks us calculate the potential difference across the LDR. Potential difference across the LDR. Now, if you see this connection, the LDR and the other resistance, they are in series. Series resistance share different voltage. They share different voltage, but same current. Now let's find current first. Current is voltage over resistance. The voltage is 9. The resistors are 1800 plus 1200. So that's 9 over 3000. So the current in a circuit is 3 times 10 times 10 to the power minus 3 amps. That's the current in the circuit. So voltage in LDR is IR, and I is 3 times 10 to the power minus 3. The resistor for LDR is 1800. When you multiply them together, we have 5.4. That's the PD across that. The next one. The circuit is now modified by adding uniform resistance wire XY and a galvanometer. The length XY from here to here, the length is 1.2. The movable connection Z is positioned on the wire XY so that galvanometer is 0. Calculate the length SZ. Calculate the length SZ. I'm looking for, let me call the length here L1, the length between XZ, and the length between Z and Y, L2. I remember we have a relationship R equal to KL. So K is R over L. When you are comparing two resistors, that will be R1 over L1 equal to R2 over L2. But what they asked us to look for in this question, calculate the length SZ. The length SZ is L1. So that will be R1 over L1 equal to R2 over, what's L2? Remember that L1 plus L2 will give us 1.2. So L2 is 1.2 minus L1. So L2 is 1.2 minus L1. So let's calculate L1. R1 is 1800. L1 is unknown. R2 is 1200 over 1.2 minus L1. Double zero cancel double zero, like this is allowed. So this is even the space. So at the end of the day, I have 18 over L1 equal to 12 over 1.2 minus L1. Cross multiply. We have 12 L1 equal to 18 times 1.2, 21.6 minus 18 L1. 12 plus 18, that's 30. 30 L1 equal to 21.6. So what is L1? 21.6 over 30. 21.6 divided by 30. 15 times 1.2 divided by 30. 0.72. So the length SZ, which is L1, is 0.72. And the next question. The environmental condition change causing a decrease in resistance of LDR. State whether there is decrease, increase, or no change for intensity of LDR. Let me quickly summarize the LDR for you. The IV characteristics for LDR, is the graph of LDR. We always plot the graph of resistance and light intensity. For LDR, the graph is always like this. You know the meaning? This part here is the bright region. The bright region always have low resistor. This one is I. The I resistor is low or darkness. That's how it works. So when it's bright, resistance is low. When it's high, for high resistance or increasing resistance is dark. So let's see what's going on here. The intensity of light illuminating LDR. The intensity of light illuminating LDR. When it's illuminating, so which means we have intensity increases. So we have decrease in resistance, and when the resistance is low or decreased, it is bright. So which means in this case, intensity increases. How about power? Remember that when the intensity increases, at that point resistor is low. Power is V squared over R. So when the resistor is low, power is high. So you have to relate a formula with power and resistor. So in this case, we have power increases. Now the length SZ, so the galvanometer reads 0. The length let's see the length. Remember that intensity is power over area. Intensity, power over area. And area can be volume times length. So I can say intensity and length, they are inversely related to each other. So when intensity is high, the length is low, it decreases. So length decreases. That's it. Then to the next one. The last question. Nucleus P and Q are isotopes of the same element. Nucleus Q is unstable and emits beta negative to form nucleus R. Okay, nucleus Q emits this to form R. So let's assume something. Let me say if P is 12 6 carbon, Q is 13 carbon 6. Let me assume that. Compare the number of photons. Compare the number of photons. The number of photons is the same. That's the atomic number. The position of the element. So it is the same. It does not change. Number of neutron. 12 minus 6 is 6. 13 minus 6. 13 minus 6 will be 7. So the number of neutron are not the same. They are unequal. They are not the same. That's it. When nucleus Q decay to form R, the quark composition of the nucleon changes. State the change of the quark composition. It changes. Okay. Now let's see this. Q decay to form R by emitting. So normally neutron, when it changes to proton, it does that by emitting beta negative, yeah, and anti-neutrino. That's the whole idea. Whenever beta negative is emitted, it happens when neutron changes to photon. So state the change of quark composition. And neutron has no charge. Neutron has no charge. Photon has positive charge. So since for neutron, the quark composition, since it has no charge, will be up, down, down, How? Because up is 2/3 electron. Down is -1/3 electron. Down is -1/3 electron. When you do this together, the LCM is 3. We have 2 minus 2e minus e minus e. So we have is it up, down, down? Yeah, this one have 2e minus e minus e, 0e/3. It give us 0. So the quark composition for neutron is up, down, down, because it's up. The combination of up, down, down is the one that give us 0 charge. And proton has a charge, positive charge. The quark composition for proton will be, I think, up, up, down. How? 2/3e plus 2/3e. Down is -1/3e. This one gives us 4e minus 1e. That's 3e/3. It gives us 1e. That proves the charge of photon, positive 1. So the quark composition of the nucleon is up, down, down to up, up, down. That's it. State the name of another particle that must be emitted from Q in addition to beta particle. That's anti-neutrino. Anti-neutrino. I said it earlier. So yeah, it's there. Anti-neutrino. Yes. A hadron consists of 2 charm quark and 1 bottom quark. 2 charm quark. Charm quark is the up quark, that is as in is 2/3 electron, and 1 bottom quark. 1 bottom quark is the down quark, that's -1/3 electron. So at the end of the day, so what do you have? 4e/3 minus 1/3e. That gives me 3e/3. What do you have? Plus electron. Plus 1 electron. That's it. So please subscribe to my YouTube channel. I'll be dropping more interesting content. Please share, like, and recommend to friends. See you soon.